Okay, so as the screen slowly raises, I'm going to try to figure out how to do this without that. Let's say, so if we're doing what's called Factorial ANOVA today, and let's say you have a situation where you have, I don't know, let's say levels of processing. You know about levels of processing, different, or even, well, actually it starts with retention intervals. You're doing a memory experiment, and you've got 3 groups, and you're trying 3 different retention intervals, right? So 5 minutes, 1 hour, 24 hours, right? So you got 5 minutes, 1 hour, and 24 hours. And you test them on their memory, and that's fine. And that's a perfectly reasonable experiment. It's not like it's a good experiment or a bad experiment, but it is an experiment, and whatever, okay? You do the ANOVA, you find out you've got a significant effect, everybody's happy, nobody's dead, and nobody wrecked a projector. Now, what about doing something like, what about, might my voice do that? I don't know. What about doing an experiment where you had different levels of processing? Levels of processing, shallow, medium, deep. Some of you took memory with the ANOVA last year. You know about this stuff, so you know that you could, if you process something shallowly, like count the number of vowels or something like that, it doesn't work nearly as well as something that's done more deeply, think with a medium. So instead of doing 5 minutes, 1 hour, 24 hour, we do low, medium, and high levels of processing. And you find high levels of processing that works better than low levels of processing, blah, blah, blah. It's not really mind earth-shattering. That's a result that's almost as old as me. That is not your honors thesis. And it's perfectly fine. There's nothing wrong with the experiment. The thing is, what level of processing should you do the experiment, should you do this experiment at 5 minutes, 1 hour, 24 hours? And frankly, what level of processing, what retention interval should you do the level of processing experiment at? I don't think there's an answer to that. Right? There isn't a great answer to either of those questions. So what we could do is combine the two, which is what we do with factorial analysis of variance. So instead of having, so we have 5 minutes, 1 hour, 24 hours, and then we have low, medium, and high levels of processing, and you have one group here, different groups of people, right, getting different, levels of processing. So that's how you do this experiment. And I mean, you won't do that, I think, in advance anyway, but this is how you would do this experiment, is you would do what's called a 3 by 3. In this case, factorial experiment. So, you know how we have a model in simple analysis of variance, x equals mu plus tau plus epsilon? Well, we have something similar here. We have x, so that's any score, equals the grand mean. We have that again, of course, with the grand mean. Now we have 2 different effects. We had tau before, we're going to have 2 of those. And we're going to call them alpha and beta, and I'm sorry that they're called alpha and beta, because there aren't the same alpha and beta from power and from type 1 and type 2 error. Right. So any score was the grand mean plus the effect of A plus the effect of B, because there's 2 variables. Okay. Plus the AB interaction. So the only new thing we have in there is this alpha beta term. We have 2 what are called main effects, A and B, or in our case, we'd say A was levels of processing and B is retention interval. And we have error still. We just have this one extra thing, this alpha beta, which is the interaction. It's A and B coming together. A and B coming together, okay? Questions so far? Okay, good. So we're not going to only look at A and B. We're going to look at how A and B act together or how they interact, hence the term interaction. That's what we're going to look at. It's sort of a whole is more than the sum of its parts kind of thing. Okay? It's the whole is more than the sum of its parts. So basically, it's these two things coming together or interacting. So it's the effect of one variable changing depending upon the level of a second variable. The effect of one variable changes depending upon the level of some second variable. So there's clearly going to be an effect that we know is an effect of retention interval. The difference between 1 hour and 24 hours is, with a thing like this, if I give you a list of words, that's maybe it's probably more striking if I did 5 minutes and 1 hour, right? Give you a list of 10 words, 5 minutes, you'd be pretty good. 1 hour, you'd not be so great. But if I give you, if I said, think about the meaning of each of these words, you're probably going to not, there's probably not going to be quite as much decay. Does that make sense? There's not going to be as much decay. So the effect of one variable, that's the effect of retention interval, changes depending upon the level of a second variable. Okay? So we could, and in the notes there's a graph. Let's think of that's a very simple example. In fact, we often see things like this. Let's make that. Yeah, let's do that. Something like this. So we have a variable along. We have the fingernail. That's horrible. Variable along the x-axis, and we have a variable. And we see that the differences between the B's, B1 and B2, is different at A1 than it is at A2. There's something else going on other than just what are called the main effects of A and B. Okay? Questions? Good so far. This is really important that you get this. That's why I'm so frustrated with the projector not working properly, because this is really important. Okay, good. If you have questions, please ask them. So all I'm saying, as I just said, is the differences between B1 and B2 are different at A1 than they are at A2 in this case. That's what an interaction is. So let's go back to the model, x equals mu plus alpha plus beta plus epsilon. Sorry, alpha plus beta plus alpha beta plus epsilon. We have some assumptions. We're always going to have assumptions, right? So the first assumption is that the sum of the alphas equals 0. All that means, and also let's bring the other ones up here on my screen here. The sum of the betas equals 0, and the sum of the alpha betas equals 0. All that's saying is that if all the scores at, say, A1 go up by 3, because they're in A1, that means all the scores at A2 go down by 3. They have to sum to 0. You'll see in a moment that it can't not work like this. It's literally mathematically impossible for them not to sum to 0. It can't happen. So same thing with the B's, and the same thing with the AB. So if being let's draw a picture here, not a picture, but a little table. If A1 makes you go up 1, A1, B1, then A2, B1 makes you go down 1, then A1, B2 makes you go down 1, and A2, B2 makes you go up 1. Those could be 7s or 3s or 72.6s. But they have to sum to 0. So again, the same thing with just being in A1 regardless of B. It could be a +6 and -6. and B1 and B2 could be minus 3 and plus 3. It doesn't matter. This has to sum, they all have to sum to 0. If they don't, you've made a mistake. It can't not work this way. Like I said, this will become, I think, pretty apparent as we go along. So those are just assumptions of the model, and I can tell you, by the way, that one of the assumptions of straight-up vanilla analysis of variance that we started with was this: the sum of the taus equals 0, if you remember. The sum of the treatment effects equals 0. So that's all. That's just an extension of that. Error is normally distributed. It's normally distributed and independent with a mean of 0 and a variance of sigma squared sub epsilon. So error is normally distributed independent. And again, that was something with regular old analysis variance. Error was normally distributed and independent. We can probably violate the normality. In fact, I know we can. We can't violate the independence. And that just depends on every score. If I know your score, I don't know your score. If I know your score, I don't know your score, etc., etc., etc. Okay? Good so far? This is good. This is good. Now, so those are assumptions about the model. There's assumptions for F, a homogeneity of variance, so all the means, so all these groups here in our mythical experiment of levels of processing and retention interval, those all have equal variance. We can violate that a little bit. Homogeneity of variance means by times 4, as long as one isn't 4 times bigger than another. We talked about transformations the other day. You could often do a transformation to fix this. We have random samples. Don't worry about that. We can violate the hell out of that. We have normal populations. Okay? And again, we don't have to worry about that. We don't hardly ever have normal populations. We can violate that. The big thing we can't violate is independence of observations. And we try not to violate, excuse me, we try not to violate homogeneity variance too much. We violate a little bit. But a factor of 4 doesn't really affect anything as a rule of thumb. Any questions I can answer so far? You've all seen designs like, well, you took 2127, right? You've all heard about interactions and seen designs like this. Not too scary. Okay. Some of you look a little scared. I can see by your eyes. Can't see your mouths. Which is good, I should say. So let's think of a numerical example. Now I'm going to give you the example I have here. I'll draw it up on the board. For those of you watching this later, the projector didn't work, and I'm recording this, but I'm also using the blackboard because it's 1973. So this is kind of a numerical example. We can call it a numerical example. But I'm not going to have all the different means or different scores for individuals. Just like, remember we worked on a numerical example the other day when we did regular analysis of variance, and I didn't talk about the individual scores because it's just too much arithmetic. Okay, so that's the only reason I'm doing this. It's just too much arithmetic. So, 9, 7, 3, 1. I don't know what I'm measuring. I don't know. I don't know. These are just scores. I don't know what the experiment is. I don't know what A and B are. They're just independent variables. That's the independent score. What we're going to do is we're going to break this out so we can find all these effects. Now, we have something that applies to every single one of these cells. And the thing that applies to each and every one of these cells is the grand mean. It's the same for every cell, right? Does that make sense? Yes? Really stop me if it doesn't make sense. Okay. So the grand mean is what? 9 and 7 is 16, and 3 is 19, and 1 is 20. So it's 20 divided by 4, because it's 1, 2, 3, 4. So it's 5. The grand mean is 5. We're going to take 5 out. So we're going to take 5 out from all of these. And so what we're going to end up with is 9 minus 5 is 4. 7 minus 5 is 2. 3 minus 5 is negative 2. 1 minus 5 is negative 4. The grand mean is gone. Now take a look at this. Do you know how that sums to 0? Right? Add those numbers up, they sum to 0. Okay? We've taken out the only thing that applies to all the numbers, the grand mean. If we do that, those numbers must sum to 0. They have to. And I can give you a very simple example. The numbers I have, you might think, oh, Dave, cook these numbers. Oh, see, holding this makes me want to break it. If this was in my house, this would have already been at that wall. Actually, not anymore. I did a lot of therapy for anger, so I'm a lot better now. Yeah, this is the non-intense me, by the way. Evan, what do you weigh in kilos? Roughly.
80.
Yeah, okay. I weigh about 90. I should probably weigh 82. This is the problem. Let's pretend I weigh 90. Okay. So between the two of us, our weight, 90 plus 80, 170, right? 170 divided by 2 is 85, correct? So if we take 85 away from your weight, now we have negative 5, or we take 85 from mine, we have 5. Hey, look, it's sum to 0. I didn't cook up those numbers. I guess I'm going to just use 85. So it's going to sum to 0. So we have left here is 4, 2, negative 2, negative 4. So all we have left are the effects of A. Look, this is gone. And we don't have this. Error's gone. So all we have now is, hey, wait a second, I have to cross them out. I could use an eraser like it's 1973. It's not even like a whiteboard, it's a blackboard. It's like an elementary school again. If it was elementary school, I always would have challenged the teacher 4 times on facts she got wrong. I was a real peach to teach. We got this left, and this left. Okay, good. Well, let's find out some of these. Well, let's for B1, oops, sorry, over here. The average is, the total is 6. For B2, it's negative 6. So the effect of B1, the effects of B1 and B2 are 3 and negative 3. Because there's 2 of them, so I'm just dividing by 2, just like I did with our weights. And now what I'm going to do is I'm going to take 3 out of all the B1s and take negative 3 out of all the B2s. So if we take 3 out of all the B1s, what do we get out of all the B1s? Take 3 out of that, we get, this is labeled. Okay, take 3 out of these. 4 minus 3 is 1. 2 minus 3 is negative 1. We're going to take negative 3 out of here. Negative 4 minus negative 3 is negative 1. Oops, that should be a negative 1, sorry. And negative 4 minus negative 3 is, I made a mistake. Oh, no, negative, that should be plus 1. Negative 2 minus negative 3, that should be plus 1. Oh, yeah, okay, I see that. Or did I? Oh, that's right. Yeah, negative 2 minus negative 3 should be plus 1. And negative 4 minus negative 3 should be negative 1. Okay? So now let's look at, do you see what I did there, even though I quickly confused myself? Well, now what we're going to do, what do we have left? Well, let's see, we can now erase the, with the B's done. Now what we have left is the A's, the alpha effect, and the alpha beta effect. Well, let's sum across. Oh, you can also prove to yourself that the B's gone. Look, 0, 0. See that? It's gone. We took it out. So the effect, the main effect of A, so it's A1 is 1, because 2 divided by 2 is 1. The simplest division fact you ever learned in your life. Back when you first learned division, you thought you were proud of yourself to go to school and said, hey Dad, 2 divided by 2 is 1. Your dad looked at you and said, it gets harder. I hope that's not what your dad said. That's not very encouraging. Let's do the same thing as we did before, but take out the A's. We'll take out the 1s and negative 1s, take out the A's effect, 8 effects. We're going to take 1 out of all the A1s and negative 1 out of all the A2s, and we're going to be left with a bunch of zeros. So this is gone. The only thing left is this, is alpha beta, except they're all zeros. So that means we have an A effect. With B effect, we have no interaction. We have no interaction. Okay, questions. Do you see how I got how we got here? Yeah? Good so far? You're okay? Yeah. Jared. Okay, so what's the end? What are you doing?
I understand. Like I kind of between looking at my laptop
Yes.
And looking back at you and
yes.
Sleep deprivation kind of lost you for a minute.
Fair enough.
I saw what you did with the beta effects.
Yes.
And yeah. Okay.
I just did the same thing.
Just so I can be like, where are we getting 3 and negative 3?
Because I took 4 and 2 is 6, negative 2 and negative 4 is negative 6, divide them each by 2 because there's 2 observations. I'm getting the average effect of B and B1, the average of B and B2. B1 raises your score by 3. Yes. B2 depresses your score by 3. Does that now make sense?
Yes.
I see a nod, but was that just a nice nod or was that a real nod?
No, I get it.
Okay, good.
You're still taking it out by using the average.
Yeah, exactly.
Sorry.
Yeah, no, please don't be sorry. This is what I want you to do. None of us are sleeping. There's a giant pandemic, and also, I don't know if you've seen the news. You're in the Army, right?
Yes.
Okay, just make sure everything's okay. See what you can do. Talk to a couple generals.
Yes.
Yeah, just make
Yes.
a couple calls.
I, the notebook private, will
Make a couple of calls.
Let them.
Remember, you line up behind Jared. He took an oath. All right. Other questions? So this is basically, you know what these actually are? These are, if we took these and squared them and summed them, they'd be sums of squares for A and sums of squares for B. Oh, please.
Why do we want to get down to 0? Like, what's the...
Oh, why? We don't, it's not necessarily that we want to. All we're doing is we're taking everything out.
But why do we have to take it?
Because what I'm trying to do here is show you that there are, we can isolate the effect, just like analysis of variance does, of A and B and A by B.
Okay.
So we're trying to find out, and in essence, this is what it does. If we worked out the sums of squares for A, the sum of squares for A is in fact, well, it's going to be 2, because it's 1 squared, negative 1 squared. The sum of squares for B is going to be 18. 3 squared plus negative 3 squared. Sum of squares for AB is actually 0. The world is never not quite that simple. So we can partition the sources of variation. Just like in that, what we're doing here is we're doing analysis of variance, but we're doing it in a very sort of mechanical fashion. We still are really doing analysis of variance. We're actually not going to do the F-test here. We don't have any way to calculate mean squared error here because I haven't done the individual scores. But we can do it with the means and see what happens. You could even draw yourself a graph. Where's the original scores? Oh, so it's 9, 7, 3, 1. B1, B2, so it's going to be 10 and 5 and 0. A1, B1, 9 and 7. That's B1. And then 3 and 1, right? 2. One of the shortcuts you might have learned in like research methods class in 2127 is if the lines are parallel, you have no interaction. And the lines are parallel. I mean, you're pretty close to parallel. I drew that freehand in the black portion, so that's perfect. Questions? Okay. Let's do another one. What the hell? We'll practice. So, use this A and B because we have it written here already. And we have what? We have 20, 0, -10, and 2. Cool. We'll do the same thing. Let's get the grand mean. 20 plus 2 is 22, minus 10 is 12. So it's 12 divided by 4, which equals 3. So we're going to take 3 out of every single cell. So let's do that. So we'll take 3 out of every single cell. Oh, look, we already have this set up, which is nice. So what do we get? We get 17 minus 3, and 10 and negative 13. Yep. And 2 minus 3 is negative 1. Yep. So let's remove the grand mean. Yeah, 17, negative 13, negative 3, negative 1. Now the effect of A. Let's do the effect of A first, and then the effect of B first, okay? So we'll do this. Excellent. 17 minus 13, so we get 4, negative, oh look, they sum to 0. If they don't sum to 0 on the quiz you do on Thursday, this is a rather large hint what the quiz is going to be, you're going to get one of these and I'm going to ask you to do it. That's the quiz. Is that clear enough? The world's falling apart, I may as well start giving you answers. If we make it to Thursday, it's going to be fine.
Have you bought a shotgun yet?
No. I figure I'm just going to use my wit. My wits. So I'm going to outsmart the enemy, and I'm also going to make him laugh and be funny. I actually have a friend who lives in Moscow, and he's really upset. It's wild stuff. Weird, wild stuff. So if you do that on Thursday, if the world's still, I lived through the 1980s. This is what our lives were like. This is why so much of our music was about this stuff. Because it was that and Well, drugs and alcohol, which got us through these. That's what we did. So, but when you do one of these, I mean, it's obviously, it would be obviously the same. If you do this, if it doesn't sum to 0, you made a mistake. It can't not sum to 0. Okay. So we got 4, negative 4 for the A, so what is it? It's going to be 2 and negative 2, right? So let's take 2 out of A1 and negative 2 out of A2. Does everyone see how I got that? So let's just take 2 out from each of these. So we get what? It's going to be 17, so minus 2 is 15. And negative 13 minus 2 is negative 15. Negative 3 plus negative 2, or plus 2 is plus, sorry, negative 13, negative 3 minus negative 2, negative 1. And that's going to be plus 1. The leftover minus there. And again, you can always double check yourself at every single step. Once you've taken out the grand mean, do all these cells sum to 0? Yeah, they still do. Yep. 15, negative 15, negative 1, 1. So for B, what do we get? If we sum across A, for B we get negative 14, or sorry, 14 and negative 14, that's 7 and negative 7. Right? Because it's divided by 2. Because it's divided by 2. Right? Divided by 2. 15 minus 1, 14. Negative 15 minus 1, negative 14. Or plus 1, I'm sorry, negative 14. So 7, negative 7. So we're going to end up with, last time we got all zeros. This time we're going to end up with 8, negative 8, negative 8, and 8. Oh, now that, see this? We've taken out A, we've taken out B, we've taken out mu. We've got this left over, alpha, beta. There's an interaction. So over and above the effect of A and the effect of B, there's a separate effect of AB. There's a separate effect of AB. Yeah, so we have an interaction. And again, the effects here still sum to 0. And for interaction effects, they have to sum to 0 altogether, but also, you know, horizontally and vertically. And they do. So it made mistakes. And sum of squares interaction, if you were interested here, would be what? 8 squared plus negative 8 squared plus negative 8 squared plus 8 squared. So 64, 120, 256. Yes. Why don't you just find my really my mark? Probably. Questions? Yes, please.
Wait, so how do we know if there's like an effect between A and B? If it doesn't equal out to 0 at that?
Yes, if there's something left over, because we've taken everything else out, the only thing left is AB.
Okay.
So we must, got it? Make sense? Excellent. I thought I saw a light bulb there. I wasn't sure. One of the neat things about teaching this course is you can literally see people get things. You see people go, oh. It's kind of cool. Even with masks on, I can actually usually see people surprise themselves. Oh, well, I get it. If it was just zeros, we have no main effect. Oh, sorry, no interaction. We could, do I still have it up here? I do. Let's just graph it to see if we have our interaction, just to double check. When I used to do these when I was a young lad, I would usually graph them first. you can do it either way. The graphing at the end or at the beginning is a way to double check. The arithmetic is really more important. But if we've got 20, so we've got to just change the scale here. 20, we've got 10, and then negative 10. So, so for B1 we got 20, 0. Here's B1. And for B2 we got negative 10 and 2. Yeah, I think those lines cross. I think those aren't parallel. Those aren't exactly parallel lines, get across. So we have an interaction. And we have an effective A and an effective B. We've got all the possible effects. So how do we interpret these things? Because A's and B's and adding things up, that's all just, what am I looking for? Well, that's all sort of academic. It's all just arithmetic, really. We want to know how we use this to interpret results, right? So if you're going to interpret main effects, what are called main effects, that's just the effective A or just the effective B. In the presence of an interaction, it might be kind of hard. In fact, take a look at this. Would you be comfortable saying, and we found effects of A and B, didn't we? Would you be comfortable, look at this graph, in saying that A1 is always bigger? Is it A1 bigger than A2? I can't even remember. Yeah. A1 is always bigger than A2. Well, no, it's not really, kind of, sort of. A1 is bigger than A2, but is A1 always, well, except if it's B2. It's hard to do, right? In fact, I don't think you can in this case. So statistically, yes, you have a significant effect. No one's denying you have a significant effect. But you have a significant effect, but you have no, but the interaction makes it hard to interpret the significant effect. When you have something which is called an ordinal interaction, like our first one, so it looks sort of like this. I feel very comfortable saying B2 is always bigger than B1 in that case. I'm very comfortable with that. It is bigger, the difference is bigger between 2 and 1 at A2, in our example here on the board. But I'm still pretty comfortable saying it. You see what I mean? Some people will tell you never to interpret interactions in the presence of main effects. I'm sorry, main effects in the presence of interactions. I think that's a little crazy. I think that's going overboard personally. But the other people have different approaches, and it doesn't make them wrong. We just have a different way of looking at things. But with what's called an ordinal interaction, this is ordinal. The order of the main effects is preserved. With an ordinal interaction, you can do it at least. Some people say not to do it, but at least I feel comfortable doing it. I don't feel bad about it. With a disordinal interaction, like the example that we just finished, I don't know how you do that. I don't know how you talk about main effects in the presence of an interaction here. So that's a disordinal interaction. An ordinal interaction is one where the order of the main effects is preserved. A disordinal interaction is one where the order of the main effects is not preserved. So it's almost impossible. Like I said, I can do it statistically, but I don't know that I can do it in how the real world works, if that makes any sense. Questions up to this point that I can answer? Anything you can answer? Okay. So let's take apart, let's partition the sums of squares and the degrees of freedom. Partition the sums of squares and the degrees of freedom. So remember the model, x equals mu plus alpha plus beta plus epsilon. Right? And that should tell you how this is going to work. So it's going to be the sum of squares total is going to equal the sum of squares for A plus the sum of squares for B plus the sum of squares for AB. And then, of course, error. So let's think about what do these different terms mean. The sum of squares for A is the sum of the squared deviations from the mean, the grand mean, that happen because you're in group A1, group A2, group A3, whatever. Same, they're just basically treatment effects. They're like sum of squares treatment, except this time we have two treatments. So sum of squares B then, we could call them, let's say, the row means or the column means, whatever. So if we've got A along the top, that's the column means. B along the side, those are row means. So we know the row means and how they deviate from the total. Column means and how they deviate from the total. So remember the other day I said we had our different groups, and I said each group's mean deviated from the grand mean. That's exactly what this is here, except instead of it being just individual groups, it's people in A1. They can also be in B1. People in A2, they can be in B1 and B2. So again, if our design looks like this, A1, A2 along the top, B1, B2 along the side, the sum of squares for A is these means here. The sum of squares for B is these ones here. How much do these scores here? So we get a score here, we get a score here, we get a score here, we get a score here. How much do these two deviate from the mean? How much do these two deviate from the mean? Okay? Now the sum of squares for AB, that's the interaction, is how much do these individual cell means, are called cells, A1, B1, A1, B2, A2, B1, A2, B2. A2, B2, of course, a really lousy robot in Star Wars. You never hear about it. Thank you. Thank you very much. How much those individual cell means deviate from what we would expect based on the effects of A and B. What's left over? If you want to think about this in concrete terms, men are paid less than women. Or sorry, more than women. Right? I don't think it's good, but it is. Estimates range between, what, 15 cents on the dollar, maybe 20 cents on the dollar. Depending on the job, some jobs it's a lot better, but it depends on the job. But men are paid more than women. It's wrong, but it's true, right? So there's an effect of being a man. You get paid more. White people are paid more than non-white people. Good? No. Is it true? Uh-huh. point being a woman who's also a visible minority is extra hard. That's an interaction. That's an interaction. So you want to think of a concrete example. I think that's a good, because it's a happy one, but it's one I think we all know is a thing. You sort of keep it in mind. And again, obviously, these are all average. You don't say, yeah, but what about that? Yeah, fine. Believe me, disabled people are paid like shit. People with vision like me have an unemployment rate that starts with a 9, and it's got 2 digits. I mean, on average. I do fine, but not as well as I'd like, but you know, almost paid what I want. So you can think of interaction as, it's a depressing example, but I think it's one we all know about. That's why I'm using it. And let's use that depressing example to, you know, rather than all the other depressing things in our world right now. And of course, sum of squares error in the end is just the individual scores from their cell means, and we don't even have the individual scores in there because I'd have to be writing all kinds of little numbers. And I don't think it helps you understand anything. Any questions at this point? I think you guys are doing great. Maybe I should always just use a blackboard. Chalking. Usually when I end up using the blackboard, I've decided that day completely not thinking, wearing a black t-shirt and black pants. You just cover it. That's what So now more precisely, I'm not going to write this out, but basically you can talk about the different means. So row means from the grand mean, column means from the grand mean, cell means from the mean you would expect due to the fact that we have an effective A and B, and then individual scores from the cell mean. So let's look at the degrees of freedom. So we have to worry about how you calculate those things, because basically we don't do that by hand. Any design has this many degrees of freedom, big N minus 1. Okay? Now, when you think about treatments, we used to talk about how when we said treat was number k minus 1, right? It was number of treatments minus 1. Well, we've got 2 of those. Levels of A minus 1, levels of B minus 1. That's our degrees of freedom. Levels of A minus 1 and levels of B minus 1. The weird one is this. Sum of squares AB. Now think about what it's about. It's about deviations of cell means from what we would expect if there's an effect, you know, we expect due to just the row means and the column. So what if we fix here? We fix 2 things. We fix the mean for A and the mean for B. Let's just do this as a bit of a thought experiment. So let's just do a very simple design, an A by B, 2 by 2. So give me a number for the effect of A1, B1. Like positive, negative, but just some number, doesn't matter. Okay, 6. Put it here. Oh, negative 6, 6, negative 6. Oh, I couldn't. I was really constrained there. I had 1 degree of freedom in that case, didn't I? I could put the 6 anywhere, but after that, everything had to be a certain number. But let's make it a bit bigger. Let's make A3. Where do you want me to put the 6 this time? How about A3B1? Oh, that has to, okay, that's good. Can we put another number somewhere? I think so, eh? Give me another number. There's no right answer to this. Give me a number.
4.
4, thank you. Where do you want me to put it?
B1,
4. Perfect. Oh, something happened. What does this have to be here? It has to be negative 10. It has to be. Because this has to sum to 0. So this one and this one here we fixed. Well, this has to be negative 4. This has to be positive 10 because it has to sum to 0. This has to be negative 6. So these sum to 0. That sums to 0, 0, 0. Wait, 2 degrees of freedom that time. We'll do one more. These arrays are garbage. Let's put a 3 here. Let's put, I don't know, negative 4 here. Let's still put another one. Put a 2 here. Sure. How about a negative 2 here? Uh-oh, we're at 100 degrees of freedom. This has to be, now this has to be what? Well, this has to be 0. Because this has to sum to 0. Oh, this has to be negative 3. Because this has to sum to 0. Negative 4, negative 2, 6. What's this have to be? Positive 6. Because it has to sum to 0. This has to be 6 minus 3, so that's 3. This has to be another negative 3, right? This has to be 2 minus 3. This has to be positive 1. Oh, look, it works that way too. That time made 4 degrees. And you can tell again, I'm not cooking, except for whole numbers, I'm not cooking anything there because if I did, how would I remember all that in my head? I can't. They must sum to 0. So this time we had a 3 by 3 table and we got 4 degrees. Turns out that we have A minus 1 times B minus 1 degrees of freedom for the interaction. Now for the sum of squares error, within each cell, we have n minus 1 degrees of freedom, little n minus 1. Number of observations in a cell minus 1. And we have A times B cells. So it's A times B times n minus 1. And if you feel like proving that A minus 1 times B minus 1 plus A minus 1 times B minus 1 plus A times B minus times n minus 1 equals big N minus 1, go nuts. Stuff I heard you. You can do it yourself. That's the kind of algebra you used to do in like grade 7. Questions so far? Okay. Here, Richard. So let's think about the expected values. Yeah, let's finish with that today. Remember when we did the stuff on straight ahead ANOVA, one-way ANOVA, and the expected value of mean squared treatment? Remember that? Was treatment plus error, right? And the expected value of mean squared error was just error. meant that we could then take mean squared treatment divided by mean squared error and the summary table, and we would get the isolate treatment, right? Okay. Well, what we have to really do the same thing for mean squared A, mean squared B, mean squared AB. And of course, mean squared error. Well, the expected value of mean squared A is the effect of A plus error. The expected value of mean squared B, should not surprise you, is the effect of B plus error, beta plus error. You can all see that. The expected value of mean squared AB, or the mean squared interaction, equals that, alpha beta plus error. And the expected value for mean squared error is, well, error. Yay! So now this tells us what to divide by what. Right? We take mean squared A and divide by mean squared error to isolate alpha. We take mean squared B and divide by mean squared error to isolate beta. We take mean squared AB and divide by mean squared error to isolate alpha beta. So there's going to be 3 f-tests. We can actually do 3 f-tests in one analysis. Because we find it's a main effect of A, a main effect of B, and the interaction. So we're simply going to divide mean squared A by mean squared error, mean squared B by mean squared error, mean squared AB by mean squared error. That's a lot of stuff. Oh, it's actually going slow. Yeah, it's close. Questions at this point? I know it's a lot of stuff, so I don't want to, because the next thing, everything gets weird. I'll wait till I throw everything weird at you.
It was the only thing I was gonna ask about is I looked at the big ass long written out, you know.
Oh, the sum of squares.
Yeah, all of that. That is, we went over that with the talking about how we got the degrees of freedom to do all those calculations.
Yeah. Yeah, and those are things, I mean, yeah, it's the sum of the column means minus the row means squared, plus the row means minus all the grand means squared.
That's all.
But it's basically, that's technically where all the math comes from. But what we've done, when I did the thing when I took, at the beginning, when we took out the grand mean and then did all those deviations from 0, taking out the grand mean means there's deviations from 0 instead of deviations from the grand mean. So when we had, say, 2 and -2, that means the sum of squares for whatever that was, well, 2 squared plus -2 squared, so that's 4 and 4 is 8. That's in essence what happens. Not in essence, literally exactly what happens. Yeah, no problem. When you start to see a whole bunch of summation signs, it should be something. You should look at that and go, oh, okay. It should bother you. Other things. This is great. I thank you for your, what's the word I'm looking for, indulgence. And we will continue this next time. Okay, so I should probably go back a slide here for a sec. So, oh, that's a little off, that's fine, I don't care. The projector being a little off is better than nothing working at all. Okay. So, actually, let's go back even further. Right, the expected values, that's where we left off, right? So if you remember, for the simple ANOVA, the expected value of mean squared treatment is epsilon or error plus tau treatment. So we would just divide mean squared treatment by mean squared error to find out if we have an effect of the treatment, right? Okay. So we have to do the same thing for mean squared A, mean squared B, and mean squared AB, and of course for mean squared error. These are going to come out exactly as you would expect. I'll rotate this mic a bit. There we go. The expected value of mean squared A is A divided by epsilon, alpha divided by epsilon. So in other words, it's the effect of A, the variance due to A, variable A, plus error variance. B, well, this shouldn't surprise you, is beta plus epsilon, the B variance plus error. Interaction, alpha beta, is the variance due to the interaction plus error variance. And mean squared error is epsilon. Again, just like you'd expect. Okay. So, questions about that? Like, it's shouldn't surprise us. And what we're going to do is we're going to try to isolate. The idea here is to try to sort of isolate the effect we're interested in. So we're interested in alpha or beta or alpha beta, right? We want to know if there's an ineffective A, an ineffective B, or an interaction. We do that by division. So it looks to me like we divide by mean squared error and we're fine. We're going to do, as I said the other day, 3 F-tests, 1 for A, 1 for B, 1 for AB. Yay! Everybody's happy. And the crowd goes wild. Yay. Of course there's a however. Isn't there always a however? These expected values are only the case if you're interested in particular values of A and B. And you in your experiment, and you have no interest in any other values. So if you're doing this out of analysis, which you would do, I mean, I think all 3 of my honor students are probably, no. 2 of my 3 honor students are doing Factorial ANOVA kind of design for their honor thesis. Every year, people are doing this kind of design. It's very common. If you go to the honors thesis conference, you'll see that it's always like that. It's a very common design, the 2x2, 3x3, whatever. Then people extrapolate and they say, okay, we're interested in, what's our running example? It's retention interval and levels of processing. So retention intervals of 5 minutes, 1 hour, 24 hours. And they show you a graph, and it shows 5 minutes, and then it goes down to 1 hour, and then way down to 24 hours, and the lines are connected, and technically they shouldn't be. Because this analysis only works if those levels of that independent variable are the only levels you're interested in. You're not interested at all in the levels in the middle. What? Huh. It's actually called a fixed effects model, and in fact it is the most common kind of analysis that people use. It's a fixed effects model. What if we randomly chose the levels? Yeah, the opposite of this is going to be, it's all fixed, one's going to go random. What if we randomly chose our levels? So instead of 5 minutes, 1 hour, 24 hours, we chose 3 levels out of a hat. And we had 1,000 different possible levels. Or we wrote a computer program for better using a random number table too. Choose our different levels of our independent variables. So we got like 2 minutes, a day, and a week and a half. I don't know whatever the hell they mean. Who knows? So what if we randomly chose them? And if you think about this for a second, that's probably going to change the math that's the basis of this. It's not a source of variation, but it's going to change the way variance happens. That's probably the best way to put this. So that's called a random effects model. And the expected values for the mean squares are different with a random effects model because you've got something else going on. You're randomly choosing levels. So for a random effects model, if you've chosen all your levels of your two, let's say our two variables A and B, we've chosen them randomly. The expected value of mean squared A is alpha plus alpha beta plus epsilon. The expected value for mean squared B is beta plus alpha beta plus epsilon. Notice how the interaction is always in there now. Weird, right? The expected value for alpha beta, the interaction, is alpha beta plus epsilon. And the expected value for error, for mean squared error, is epsilon. And again, what you're trying to do, think about this, you're trying to sort of isolate what you're interested in. You want to find one thing to divide by the other, so we can only find the effective A or the effective B of the interaction. So in this case, we're going to divide mean squared A by mean squared AB, because look, all we want to isolate the A. Well, there's alpha, beta, epsilon. Alpha, beta, epsilon. Oh, okay. So just the alpha. You're going to divide the same thing, mean squared B. You divide by mean squared alpha, beta, or AB rather, the interaction mean squared. And mean squared AB by mean squared error. So the weird thing is we get two different what are called error terms in this kind of design. Error terms are what you divide by analysis of variance. Our first error term is mean squared AB, but then we test mean squared AB with another error term called mean squared error. The nice thing is, when you're playing with SPSS or any stats package, you can just tell it, is this a random effects model or a fixed effects model, and it'll do the right thing. It'll divide with the right thing. So that's good. What about we have a mixed model with A is fixed and B is random? Maybe you're thinking to yourself, now Dave, does this ever happen? These random effects models or the mixed models. I have only seen a random effects, I've never seen a random effects model, I've seen a mixed effects model in the literature I read extremely rarely. Do you have any other question?
I was going to say, like, when I mistakenly went over this part
Okay.
this morning, and
Yeah.
that says a lot about how I did on the quiz. Instead of focusing
Your honesty is tremendous, and I find it refreshing.
But mixed models, like, if you decided you needed to fix one variable in order to study just one other variable in your design, wouldn't that, then the mixed model make sense?
Here's an example, and that's I think is the example that's used in the textbook. So yeah, I think that's where I'm getting this from. A little spoiler alert: I don't read the stats textbook very often. I know it already; it doesn't change a lot. And I've been using that book for 20 odd years, different editions of it. Anyway, let's say we were interested in tire wear. That's in the book, and we're interested in different tire compounds. Right? Some tires are harder than others. I don't know if you follow motor racing. One of the big questions every week in Formula One is what tires are guys going to race with? So some tires are soft, some are medium, some are hard. That's 3 levels. Those are the only 3 levels you're interested in. That's a fixed effect. But let's say we're not racing car drivers. I don't think any of us are. Anybody here a Formula One race car driver? I don't think so. So, Max Verstappen is in this class? I don't see Lewis Hamilton anywhere in here. Anyway. Nikita Mazepin isn't racing anywhere anymore. Anyway. We have 3 tire compounds. 3 tire compounds. But we have, it's in Canada. We have different cities that have way different climates. Here we get snow. It's still snowy on the ground and minus 24 when I woke up this morning on the 3rd of March. Same province, you go to Windsor, I don't think there's any snow on the ground at all, probably. Go to Vancouver, I don't know, probably rainy, because that's all that happens there. And we went to, I don't know, let's go to Corner Brook, Newfoundland, and Labrador, where there's snow up to your head. He said from experience. So maybe in Canada, we would randomly choose, say, 3 or 4 cities. That's a random effect. entire compounds are fixed effects, the 3 entire compounds, but our 3 or whatever cities we're going to choose would be random effects. And it would make complete sense to use a random effects model and randomly choose cities because we're a tire company. We can't fund researching to have tires perform everywhere. Right? That's the case where you might see it. It's pretty rare in almost any sort of life science, in psychology or biology, to ever see anybody use a random effects model completely. It's even pretty rare to see a mixed model. So you're probably going to ask, Dave, why are you telling me this? You'll find out next week. Because there's a very special case where we have a variable that we consider a random variable. But here, this is. But here's the weird thing that happens. In this model, A is fixed. If A is the fixed effect, we have the expected value is alpha plus alpha, beta plus epsilon. If B is random, it's beta plus epsilon. And then the interaction is alpha, beta plus epsilon, and of course the error is just error. And that's not a typo. I know it looks like, well, isn't this, for mean squared A, isn't that actually the same as for random? Yeah. But you said A is fixed. Yeah. The math makes it like that, and we don't have to go any further than that, okay? So if one's fixed and one's random, we're going to divide A by mean squared AB and B by error. It's kind of wild, I know, and it's counterintuitive. And believe me, when I first learned this, I kept looking at the textbook over and over again after I took my notes and I was in class, and I was thinking, this has to be wrong. The world can't, but it does work like that. It's counterintuitive because it feels like it should work exactly the opposite, but it doesn't. Question? You look at the
You said you weren't going to go further into it, so I wasn't going to ask.
Yeah, go ahead. I can go a little bit further.
But to me, trying to make this make sense conceptually.
No, of course, that's what I want to happen. So that's good.
How I do. But so you're only accounting for, in the calculation, an interaction effect for the fixed variable
with a random.
Because it's fixed.
With a random variable.
Well,
it's interaction. It's the two variables act together.
Yeah, but you're like the calculation for the expected mean squared of A. That A is our fixed. Yeah. Okay.
It'll be A is fixed in this. Yes, that's right.
So we are accounting for the interaction effect in that one specifically because it is.
Because it's fixed and the other was random. You can just trust me that the math works out this way that's behind this.
Is there a specific reason? Why do we not account for the interaction with B?
Because B...
That's the dumb question.
No, it's a good question. I'm going to have to just say because the math behind this works out that way. It's really way beyond the scope of the course. I can show you after class, well, the book that I have all the proofs in is at home. I can bring it in if you want to see it.
Because calculus?
Yeah, because calculus, because of random sampling and things like that. Yeah, it's sort of I've joked before that if you're Catholic, I'm Pope Dave, and I just told you the way the world works. I mean, that's not going to be a Catholic joke or a Pope joke. But it just is. There's not a whole lot I can say beyond that. And that's sadly hopefully one of the few times I have to say that in this course is just it works that way. I know it's annoying. Don't misunderstand me. It bothers me because my sort of sense of symmetry is completely blown because it shouldn't work like that. But math does work that way. Yeah, because math is probably the best answer. So in this case, well, when we think about random fixed effects, what's the deal? Like, what's the deal with random fixed effects? Jokes as fresh as 30 years ago. So we're assuming with a random effects model that the levels of the random factor were literally randomly selected, and they are independent of each other. Okay? We're assuming that. So what we're usually doing is sort of a kind of random fixed, kind of random model, kind of sort of thing, kind of. But it certainly isn't the case when I choose 5 minutes, 1 hour, and 24 hours for my rotation intervals that I chose those randomly. I chose those on purpose. They're probably actually not independent. I probably did that for a reason. So we can't assume they're random, so the closest approximation is fixed. You can say, Dave, now, wait. Close approximation, I thought all this math had a whole bunch of assumptions. Yeah, but you know what? When you do a bunch of simulations, it turns out the closest thing to reality, when you have a variable that's actually fixed, but isn't really, like I said, it's sort of halfway in the middle. The closest thing is using a fixed effects model. So unless you randomly chose them, or you're assuming they behave like you randomly chose them, your level, you assume they're fixed. So you use the fixed effects calculations. If you really did randomly choose them, or you assume they're like you randomly chose them, like let's say we thought of subjects, individuals, as a variable, which we're going to start doing next week. We're going to think of that as a random variable. But we hardly ever use random effects. Well, it just isn't a thing. And in fact, when it does come up, a couple times when I've been reviewing articles for journals, and I've seen that people are confused by these things. Because it's something that comes up very rarely. And when you suggest to somebody, actually, I'm pretty sure that's a random effect. And people come back and say, yeah, the SPSS said. It's like, no, I don't care what it said. So the question I'm asking is, did you really randomly select your levels, or are you really assuming that they're behaving like you randomly selected them? And we do that with subjects. So we assume that even though we assign subjects, and we got the subjects, that they're random. Everything, we hardly ever really have random case. And we never assume, hardly ever do we ever assume they're random. Like I said, if we have 3 different cities in Canada, I think we could make a strong case that that's a random. So we end up with this, ANOVA summary table. So we have different sources of variation, right? Like we have with the regular straight-up analysis of variance. We have A and B, A by B and error. And then we have our degrees of freedom, levels of A minus 1. So let's say we get 3 levels of A, so it's going to be 2. 3 levels of B, that'd be 2. So for A by B, if we had 3 and 3, we would have 4 degrees of freedom. For error, it's number of levels of A times number of levels of B times the number of observations per cell minus 1. You're going to want to try at least to have an equal number of observations in each cell. The math doesn't fall apart without equal observations. It's just that the calculation isn't as simple as A times B times N minus 1. It's just all the N minus 1s in each cell added up together. But if they're all the same, that's just A times B times N minus 1. All designs have a big N minus 1 degrees of freedom. Big N is the total number of observations, and then you subtract 1. You don't worry about how you calculate the sums of squares because something else does that for you. But the mean square is sum of squares divided by degrees of freedom. The f-test is there, but of course the f-test works like that only for fixed effects models. If we have random effects or mixed effects, how we do the f's change. I can tell you that if I ever give you one of those fill-in-the-blank analysis of variance tables again, when I ever give you one of those again, so it's not an if, unless I tell you it's random effects, it's fixed effects. And I'm saying that because, frankly, you're not going to run into random effects, hardly ever. You're always going to have fixed effects. Okay? Questions about that?
So,
yeah, just
in order of importance, I guess, or relevance to life.
Well, none of this really.
always seeing fixed effects models
Yeah.
occasionally mixed
You
and
will-
almost never random.
Yeah, I mean, I've ran into fixed effects models, I would say like 99.5% of the time when I'm reading literature. Mixed effects, a couple of times, and I've never seen completely random effects. I've just never seen it. It happens more in things like where you're sampling a whole bunch of different lakes or something. So you might see it in, what do you call it? Sort of theoretical, sort of like population ecology, things like that, where you're looking at different amounts of, let's say, algae in different lakes, and you're choosing different lakes, and then you're all kinds of different possible treatments, and you're throwing, like, to get rid of, I don't know, some sort of invasive species of algae or some sort of algae bloom. That's the kind of place you see it. Usually it's field stuff. It's hardly ever lab stuff. It's almost always field work. So you would run into it a lot more in sort of field biology stuff than you're going to run into it in straight up behavioral science like most of us.
So in order to get actual random effects, you need a natural setting, more or less.
More or less. It's more common that way. You don't need it, but you'll have to actually either be choosing them randomly or acting like you're choosing them randomly. So when I say acting like, we're going to assume at one point that subjects are a variable. So that you're the Jared level of human, and I'm the Dave level of human, he's the Evan level of human.
So it's a subject as a level.
Yeah, we'll get there.
Okay.
Don't worry about it yet. I'm saying that eventually we're going to start considering subjects as a variable.
Only ever thought of applying levels to subjects.
No, I know. It's a weird way to think, but actually it allows us to do all kinds of cool things. But yeah, I mean, it's one of these cases where, in that case, I mean, we're not random, but it's like it's been chosen randomly in a way. It's a better explanation than fixed. Like every time I teach this class, there isn't a Jared and an Evan and there's always a Dave. Right? But every time anybody teaches a class in this room, doesn't mean there's a Jared and an Evan and a Dave. If there is, that's weird, and there's a whole Twilight Zone angle here that we have to do. So it's hardly ever going to be the case that you're going to see something with random effects or even a mixed model, but it will happen. And as I said, I have a reason I'm bringing this up. You can make these designs bigger. Oh, good. We're going away from expected values of mean squares and theoretical things. So let's get a little bit more concrete. Here's an example. This is in fact very common. This is a 2 by 2 by 2. We have 2 levels of A, 2 levels of B, and then 2 levels of C. We have group 1, 2, 3, 4, 5, 6. So we have different subjects in each group. And I'm just going to keep calling them subjects. I don't care if the NPAs want me to call them participants for all these years. And I have 2 problems with that. The first problem is I don't know why the word subject is bad. And the second thing is we're talking about statistics here, not actual people. So when they first changed that from subjects to participants, I was asked by an editor to change the subjects part of the paper I was writing to participants. And I replied that pigeons did not actually fill out a consent form. So I'm not calling them participants. Can we split the difference and call this section animals? Like, okay. Participants, they're pigeons. I don't think they're worried about the label I gave you. So, and this is a kind of design. Let's think, okay, remember we had, B1 and B2, so that's different retention intervals. Like 5 minutes for B1 and 1 hour for B2. A1 and A2, low level of processing, high level of processing. So low would be counting the number of vowels in a word, and high would be rating the word's pleasantness on a scale of 1 to 7. And what would C be? What's something else that affects memory? Group C1 has had 0 cups of coffee. Group C2 has had a cup of coffee. That's not a ridiculous design, is it? Like, I mean, that's not, it looks complicated there when you think about it. This is not wild, is it? Like, it's something you would run into. And in fact, you might see designs this big if you go to the honors thesis conference when the students present their papers. You might. I don't let my students do 2 by 2 by, like I don't let them do 3-way designs because I find it, well, I've let a couple over the years, but typically it's like, you're not trying to blow the lid off everything. Just answer a simple question. Yep.
What is that conference?
Oh, what is conference? Thesis conference. It's actually, I think we're at the end of April, which is too bad, but I think, well, it's good for the students because we gave you, I think we gave you the whole class an extension already, right past the end of the term, just because they have to collect data, that's rough. But if you're in town, theirs will be publicized. I think it's probably before the end of the exam period, I hope so. But I'm not really sure. We asked Lori or somebody else to apply. So now we have three main effects, A, B, and C. Three two-way interactions, A, B, A, C, and B, C. And we have a three-way interaction, A, B, C. A three-way interaction is when a two-way interaction changes depending upon the level of some third variable. A six-way interaction is when the five-way interactions change because of the level of some sixth variable. A 700-way interaction is the 699-way interactions changes depending upon the level of some 700th variable. Now, the best way to show this is to draw something. Oh, sorry, let's go to the model first. The model gets a little bigger. X equals mu plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. And little other things like gamma. So then we have, we have, what do we call it, the grand mean, and then we have A, B, C, A, B, A, C, B, C, A, B, C, and error. Okay. Oh, here's the picture. So this is a three-way interaction. So let's just ignore the picture on the right, the panel on the right. Let's just look at the one on the left. It seems that if we look, let's see, we've got an interaction here because look, the effect of A is bigger here at B2 than it is at B1. Right? And then look at the panel on the right, and then here, in fact, it's the opposite. A2 is bigger than A1 at B1, but then it flips at B2. So the interactions, the two-way interactions, are different depending upon the level of a third variable. Okay? The two-way interactions are different depending upon the level of a third variable. This is not an uncommon chiasm. What if we had two different species and two different retention intervals and two different kinds of stimuli to remember? Right? So you got juncos, chickadees, so that's C1 and C2, and then we got short time, short retention interval, long retention interval, spatial information, color. My whole freaking career is based on three-way interactions. This is not an uncommon kind of thing. Now, when it gets to be a four-way interaction, I can't visualize it. Because a four-way interaction means then we would have a D and we'd have a whole thing like this, and then it happens again, but these things change. I'm not saying I can't. I have trouble thinking in four dimensions. Right? And I've never let a student, I've had students say, well, I've got this variable, this variable, this one, this one. I said, let's get rid of maybe at least one of them and probably two, please. Then we'll go from there. I have seen a four-way interaction in print once that made any sense to me, that I could understand. What? Left-handed versus right-handed. Women versus men, spatial memory versus verbal memory. I can't remember what the fourth thing was. I never read the thing. Okay, questions about those things? Because I'm going to move on to something here. We're getting close to being the end. I know this stuff gets a little heavy. It starts to get very repetitive and easy to follow after we've introduced all this stuff shortly. So. Okay. Advantage of these designs. We can study interactions. There's a lot of theories in the life sciences in general, psychology in particular, but in biology too, where our theories are about interactions. One of my favorites, thinking about memory, implicit and explicit memory. Some of you took memory with me last year. And you know that implicit memory doesn't really decay very quickly, if at all. And explicit memory decays. Right? Just move this up here for a sec, and I can draw you a quick picture. And again, unlike the other room, note how the blackboard or whiteboard actually erases. So, explicit memory is I give you a list of words and I have you recall the list of words. Implicit memory is I give you a list of words and then I have you to fill in the blank. So like if one of the words on the list was coffee, and I give you C blank blank F blank E blank, you're more likely to fill that in than you are to fill in that, which is cocoa. It's also a brown warm liquid, which is why I choose that. It doesn't mean that you can't fill that in, but you're more likely to fill in this. That is priming. It's called priming implicit memory. You can take a look at a famous paper by Helving, Schachter, Stark. Jesus, 1982, I think. And they did 1 hour, 24 hours, 7-day retention interval. They gave people a list of words. It's not exactly what you'd expect for the explicit, just remembering the words, what words were on the list, you get very quick decay. For implicit memory, which is filling in these blanks, this priming, you get that. It doesn't decay. We can say the same thing about looking at, oh, you want to make this into a three-way interaction? Yes, let's show it. Now let's do this with people who are amnesic, who have got a head injury. Their implicit memory or explicit memory is down here. They can't remember the words. You know what their implicit memory is? Right up here. They're just like us. That's a three-way interaction I just talked about. The two-way interactions change depending upon the level of the third variable. The third variable is, do you have a massive injury to your temporal lobe? But yes or no. But that's a three-way interaction. All our modern understanding of human memory is about a three-way interaction. Okay? Or one of the ways we understand memory. So we study interactions all the time, and these things allow us to do that. A lot of our theories start out with interactions. The reason Tolkien, Schachter, and Stark looked at differences between implicit and explicit memory is they said, I think it's going to be different depending on the retention interval. Let's test that. Like the theory started out with an interaction. These are relatively simple to interpret. I know right now you're thinking, yeah, you're full of shit, Rod. Back then it don't seem so simple to me. But actually it's not that hard. I hope the example with the implicit and explicit memory shows you that, in fact, when you put names to variables, it's like, oh, okay. Once you've done this a few times, it's actually not that bad. It really isn't. And most of the time, you're going to deal with this, and if you do see that again, the thesis conference, assuming blah, 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 what it is, you'll see that many of the students are looking for interactions. Main effects too, but interactions. When you're dealing with complex living things, it's always about interactions of variables. Right? We're not doing physics. We're doing hard science. And by that I mean it's hard. There's got to be some downsides. Is it fixed, random, or mixed? Which is something we just go, yeah, whatever. Now, the thing is, we actually can kind of brush that off because simulation we showed that the best approximation of reality is usually a fixed effect model. And it's only going to be random if it's truly random, or something we're treating as random. These things can get really big really fast. So remember we went from, well, let's go from the simplest, x equals mu plus tau plus epsilon. And then we go to x equals mu plus alpha plus beta plus alpha beta plus epsilon. And then we go x equals mu plus alpha plus beta plus gamma plus alpha beta plus beta gamma plus alpha beta gamma plus epsilon. Okay. Let's see how big they get. Let's have a 4-factor design, which again, as I said, I think I've read one paper and I clearly couldn't even remember it. It had to do with handedness, sex, memory type, I can't remember what 4 thirds was. It was literally an experiment done by my undergrad stats prof. So a 4-factor design, and we got 4 variables, then A, B, C, D. So here's the model. There we go. X equals mu plus alpha plus beta plus gamma plus delta plus alpha beta plus alpha gamma plus beta gamma plus alpha delta plus beta delta plus delta gamma plus alpha delta gamma plus beta delta gamma plus alpha beta delta plus alpha beta gamma plus alpha beta gamma delta plus epsilon. Okay.
Abbreviation, exponential growth.
Well, not quite exponential, but it's almost exponential. It doubles minus 1.
Okay.
Yeah, but it's very close to exponential. I should wear my heart rate monitor when I say that. Count doesn't work anymore. Strong. That's big, right? So now we have 15 F tests to do. We have to do an F for A, B, C, D, A, B, blah, 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 all these up to here. And there's one of our errors. That's a lot. And again, so if we threw in, what do we have, A, B, C, D, if we threw in a variable E, we now have E itself, and then it interacting with all of those possible terms. So this gets a little difficult to interpret even. Remember I said the other day about ordinal and disordinal interactions, and if the order of main effects is preserved, I call that an ordinal interaction, I can interpret it. Do you think it's okay to interpret a 4-way interaction in the presence of a 5-way interaction? I don't know. I just don't know. I don't know what I'd do if I had a design like that. I'd break it into different experiments. Or I'd figure out which, maybe 2 of the variables I can get rid of. Yeah, I don't think I want to do those. So these things get very big very fast, and they, like you said, almost exponential growth. They basically double minus 1.
Basically, or is
They double minus 1. So the only thing you don't get is another one of these. You get all of these plus 1. You lose this, and you don't get that. So you double minus 1. So they get very big. You want to do 15 F tests. Not that you would do it, the computer would do it, but you want to try to interpret that. I don't. I've been doing this since 1988. That's I'm thinking when I started graduate school. So I figured we'll say that's when I started being a scientist. So before that, I was just a punk kid. That isn't really hard. They can get very big very fast. Questions on this? It's conceivably really annoying trying to do this. So more than 3, I don't think most people do. Any questions? Because I'm fine with stopping now. I know this is very heavy. There's a lot of things being thrown in your head. All right.
Is there a table of that?
A table of this?
Yeah. And
What?
then in your slides, I can't remember, I went all the way to the end.
A table, how do you mean, like an F table?
Yeah.
So you would have source of variation, A, B,
Be
C, D.
gigantic.
Yeah, it would have all these terms, right? It would have A, B, C, D, A, B, A, C, B, C, A, D, blah, 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 blah. And again, I could work out the expected values of mean squares if I had to, probably, if they were, fixed and random.
That's okay, I can just.
No, but I'm not gonna do it. It's the first thing, because it would provide very little entertainment value. Evan?
Just the end of the first line there, that A and then the next one, they're supposed to be together, right?
Oh, yeah, alpha, delta, yes.
Yeah, okay.
Yeah, sorry about that. I've literally, and I kid you not, I made this slide here, I made this slide up in 2010, I think, and I never noticed that. Thanks. Sorry. I'm glad you noticed that. Yep, I will fix it. Right, this used to all be on overheads. Because stats, I mean, and then I finally figured out how to write Greek letters. It's like, okay, I was good on this, it's that, it's better.